Hello friends, welcome back to my channel. Today I would like to talk about the concept hydrocarbons. A hydrocarbon is a compound containing carbon and hydrogen atoms only. Examples of hydrocarbons are alkanes, alkenes, alkynes and arenes. Alkanes. These are saturated hydrocarbons. The carbon atoms are joined to each other via a single covalent bond only. They form the homologous series with a general formula CnH2n plus 2. Physical properties of alkanes. Alkanes are nonpolar, thus they are soluble in nonpolar solvents like CCl4. They are in general insoluble and less dense than water. The boiling point of straight-chain alkanes increases with the size of molecule. This is because the number of electrons in each molecule increases, resulting in the increased strength of van der Waals force. Thus, more energy is required to break these forces. Physical properties of alkanes. Continuing. For a branched alkane, if it's more volatile and its boiling point is lower than its counterpart with the same number of carbon atoms. This is because they are more spherical and have a lower surface area. Thus, less temporary dipoles can be set up and the van der Waals forces are weaker. Less energy is required to overcome it. The density of liquid alkanes increases slightly. The mass of each succeeding molecule increases, but due to the increased strength of van der Waals forces, the molecules are more closer together. This results in higher ratio of mass over volume. Cycloalkanes. These are alkanes that joined up as a ring. The smallest possible cycloalkane is cyclopropane. Cycloalkanes have 2 hydrogen less than the corresponding straight-chain alkanes. Production of alkanes, cracking and hydrogenation. Alkanes are hydrocarbons that can be produced by cracking of longer alkane chains or by the addition reaction of hydrogen to an alkene. Sources of hydrocarbons. Crude oil is the main source of hydrocarbons. It's found trapped in layers beneath the surface of the earth. Crude oil is a complex mixture of hydrocarbons, alkanes, cycloalkanes, and aromatic compounds. Note: aromatic compounds are compounds which have a benzene ring attached to it. These substances can be separated by a technique called fractional distillation. Fractional distillation is the separation of compounds by their boiling points. Different hydrocarbons have different molar masses and so they have different boiling points. Crude oil enters the bottom of the fractionating column as liquid and vapor. The liquids, less volatile hydrocarbons, are drawn off at the bottom, while more volatile ones rise up the column. They condense at different levels as the temperature gradually falls and are collected as liquids. The most volatile short-chain hydrocarbons, which are methane and butane, leave the top as gases. So here is a representation of a fractionating column where you will see different fractions at different temperatures, and the uses are also given over here. The next subtopic is catalytic cracking. After the hydrocarbons are separated, oil companies found that hydrocarbons from lighter fractions such as gasoline are in higher demand compared to the ones from heavier fractions. Therefore, something must be done to convert those heavier hydrocarbons into the more useful lighter ones. This is done by cracking. Production of alkanes from cracking. In cracking, large, less useful hydrocarbon molecules found in crude oil are broken down into smaller, more useful molecules. Long hydrocarbons are cracked by heating them to a high temperature and using aluminum oxide catalyst to form smaller hydrocarbons and an alkene. For example, hexane can be cracked to form butane and ethene. C6H14 gives C4H10 plus C2H4. Production of alkanes from addition reactions. When hydrogen gas and an alkene are heated and passed over a finely divided platinum or nickel catalyst, the addition reaction produces an alkane. The platinum or nickel catalyst is finely divided to increase its surface area and therefore increase the rate of reaction. Example, the hydrogenation of ethene. CH2 double bond CH2 plus hydrogen. In presence of nickel, we get CH3 which is ethane. Application of hydrogenation. Hydrogenation is often used in the manufacture of margarine from vegetable oil. Vegetable oil is an unsaturated organic molecule with many carbon-carbon double bonds. When these are partially hydrogenated, their hydrocarbon chains become straighter. This raises the melting point of the oils, which is why margarine is a soft solid and vegetable oil a liquid at room temperature. Reactions of alkanes. Alkanes are saturated and generally unreactive because they are non-polar, hence they are unattractive towards nucleophiles and electrophiles. Alkanes will only react with non-polar reagents in the presence of heat or UV light. The first reaction is combustion. Alkanes undergo complete combustion under excess oxygen gas to give carbon dioxide and water. For example, CH4 plus 2O2 gives CO2 plus 2H2O. Delta H equals minus 890 kilojoules per mole. In general, CXHY plus X plus Y by 4 O2 gives XCO2 plus Y by 2 water. Larger alkanes are more difficult to ignite. This is because alkanes only burn in the gaseous state, and larger alkanes have stronger van der Waals forces that hold them together. Therefore, more energy is required to vaporize it. When the supply of oxygen is limited, alkanes undergo incomplete combustion. The possible products are carbon monoxide, carbon, and water. For example, 2CH4 plus 3O2 gives 2CO plus 4H2O, or CH4 plus O2 gives C plus 2H2O. The second reaction is free radical substitution or halogenation. Alkanes undergo halogenation via free radical substitution to give a range of products. In free radical substitution, hydrogen atoms in the molecule are gradually substituted by halogen atoms. Reagent, chlorine gas, chlorine or bromine gas, Br2. Condition, the presence of UV light or sunlight. Product, halogenoalkanes, that means alkanes with halogens. Free radical substitution proceeds via a chain reaction. And here is the mechanism of free radical substitution. First step is initiation. Energy of a photon of light absorbed, Cl-Cl bond breaks homolytically. Propagation. Highly reactive chlorine free radical collides with a CH4 molecule, forming a new free radical CH3 dot. CH4 plus Cl free radical gives CH3 free radical plus HCl. This CH3 free radical attacks another chlorine molecule to produce chloromethane plus a new chlorine free radical. This can then react with another chlorine and process repeats if sufficient chlorine present until all hydrogen are replaced. And the last step is termination. Reaction ends when two free radicals collide and combine. CH3 free radical and Cl free radical combine to form CH3Cl. CH3 free radical combines with CH3 free radical to form C2H6. The products forms large amounts of chloromethane and HCl and small amount of C2H6. It's separated by fractional distillation. Products and free radicals differ due to the halogen used. Bromine requires more light, and second one, it depends on the alkane used. More number of carbon, you get more variety of products. Environmental consequences of using hydrocarbons. Alkanes are often used as fuels. This is because the combustion of alkanes is an exothermic process and produces a lot of heat energy. Alkanes are also readily available and relatively cheap. The main uses of alkanes as fuels are to generate electricity, to heat domestic houses and cook foods, to provide energy needed in industrial processes, to provide power for ships, aeroplanes, trains, lorries, buses, cars, and motorbikes. However, the combustion of alkanes can produce some poisonous gases which can act as pollutants. One such example is carbon monoxide, which arises from the incomplete combustion of alkane. Carbon monoxide is a toxic gas that will bind readily to the hemoglobin molecules in the blood. Therefore, oxygen cannot be transported to cells, and the victim will die. The carbon dioxide, CO2, produced from the complete combustion of alkane can also act as a greenhouse gas. The increasing amount of these greenhouse gases enhances global warming. Burning fuels in car engines will also oxidize the nitrogen gas in air to produce oxides of nitrogen, which is nitrogen monoxide NO or nitrogen dioxide NO2. These oxides of nitrogen is believed to contribute in the formation of acid rain. Catalytic converters can be installed to remove carbon monoxide and the oxides of nitrogen. A catalytic converter uses expensive metals like platinum as a catalyst to convert harmful pollutants into non-harmful substances. In this case, it converts the harmful nitrogen monoxide and carbon monoxide into non-harmful nitrogen and carbon dioxide gases. 2NO plus 2CO gives N2 plus CO2. The next subtopic is alkenes. These are unsaturated hydrocarbons. They contain at least one carbon-carbon double bond, and their general formula is CnH2n, which is like cycloalkanes. Alkenes can be produced by elimination of HX from a halogenoalkane by ethanolic NaOH and heat. Second, dehydration of an alcohol by using a heated catalyst or a concentrated acid. Third, cracking of a longer chain alkanes. Let's see the first method, which is elimination of HX from a halogenoalkane by ethanolic NaOH and heat. An elimination reaction involves the loss of a small molecule from the original organic molecule. In the case of halogenoalkanes, the small molecule is a hydrogen halide such as HCl or HBr. CH3CH2Br plus NaOH ethanolic in presence of heat gives CH2 double bond CH2, which is ethene, plus H2O and NaBr. The original bromoethane molecule has lost a hydrogen atom and a bromine atom. We can think of it as HBr being eliminated from the halogenoalkane. The ethanolic OH- ion acts as a base, accepting an H+ ion from the halogenoalkane to form water. And the second process is dehydration of an alcohol by using a heated catalyst, example Al2O3, which is aluminum oxide, or a concentrated acid. C2H5OH in presence of catalyst and heat gives CH2 double bond CH2 plus H2O, which is dehydration reaction. And the third method is cracking of a longer chain alkane. When large alkane molecules are cracked, they form smaller alkane molecules and alkene molecules. CH3, CH2, 8 times CH3 in presence of aluminum oxide and heat gives you CH3, CH2 4 times CH3 plus CH2 double bond CH, CH2, CH3. C10H22 in presence of aluminum oxide and heat gives C6H14 plus C4H8. Now let's see the reactions of alkenes. These are the common reactions of alkenes. The first one, electrophilic addition of hydrogen in a hydrogenation reaction, H2, and platinum or nickel catalyst and heat. Second, with steam and H3PO4 catalyst with hydrogen halide HX at room temperature and with a halogen. The second type of reaction is oxidation by cold dilute acidified KMnO4 to form the diol. And the next reaction is oxidation by hot concentrated acidified KMnO4 leading to the rupture of the carbon-carbon double bond and the identities of the subsequent products to determine the position of alkene linkages in larger molecules. And the last reaction is addition polymerisation, exemplified by the reactions of ethene and propene. Let's see the first reaction, electrophilic addition. Unlike alkanes, alkenes are more reactive because they are unsaturated and contain a carbon-carbon double bond. A carbon-carbon double bond contains a sigma bond and a pi bond. A pi bond is a region of high density of electron which is open to attack by something that carries an amount of positive charge, electrophiles. An electrophilic addition reaction is the addition of an electrophile across the carbon-carbon double bond. Let's see addition of hydrogen H2. When hydrogen gas and an alkene are heated and passed over a finely divided platinum or nickel catalyst, the addition reaction produces an alkane. CH2 double bond CH2 plus hydrogen in presence of platinum or nickel catalyst and heat gives you CH3CH3. The addition reactions of alkenes with hydrogen is called hydrogenation and is used in the manufacture of margarine. Third reaction is hydrogen halide addition HX addition. When an alkene is bubbled through a concentrated solution of a hydrogen halide, it can be either HF, HCl, HBr or HI. At room temperature, the product is a halogenoalkane. For example, ethene plus HBr gives bromoethane. With longer asymmetric alkenes, there are two possible products that could be formed. For example, with propene plus HBr can give 1 bromopropane and propene plus HBr can give 2 bromopropane, which is considered as a major product. Where two addition products are possible, the major product is the one that has the halogen atom bonded to the carbon double bond carbon atom with the highest number of alkyl groups bonded to it. This can be explained by a rule, Markovnikov's rule. The addition of unsymmetrical alkenes follows Markovnikov's rule. In the addition of HX to a carbon-carbon double bond of an unsymmetrical alkene, the hydrogen atom attaches itself to the carbon atom that holds the greatest number of hydrogen atoms. Thus, you can see here, when propene is reacted with HCl, two different products are formed. The first one, 1-chloropropane, is considered as a minor product, and 2-chloropropane, which is considered as a main product or major product. Hydrocarbons can be classified as primary, secondary or tertiary depending on the number of R groups attached to the positive carbon. The R represents alkyl groups which can be the same or different. Carbocation is formed as an intermediate when the electrophile bonds with the carbon atom. The alkyl groups have an electron-pushing effect that tend to push the electrons towards a carbon atom which carries a positive charge. As you can see here, primary ion, secondary ion and tertiary ion, it follows that tertiary carbocation is the most stable because the positive charge is neutralized by the negative charges. The charge density on the carbon atom is the least. The most stable to the least stable is shown here. Tertiary is the most stable, then secondary, and then primary carbocation. Mechanism of electrophilic addition. The mechanism of electrophilic addition that follows shows how a carbocation forms, which is then attacked by a negative ion to give the final product of the addition reaction. Let's see the mechanism for the electrophilic addition of HBr to propene. Propene plus HBr gives 2-bromopropane. Here you can see a secondary carbocation forms and is attacked by the Br- ion to form the 2-bromopropane. The mechanism of the electrophilic addition of bromine to ethene. The double bond is attracted to Br+. Therefore, a carbocation is being produced and Br- get attracted to the positive carbocation to form dibromoethane. Addition of steam H2O, which is called hydration. Reagent steam condition: heat the gaseous alkene at 330 degrees Celsius and 60 atmosphere in the presence of phosphoric acid H3PO4 as a catalyst. Product: alcohols, compounds that contain OH group. In the hydration of alkene, steam is added across the double bond. Ethanol is produced. The detailed mechanism of the reaction is as follows. Step 1. Formation of a carbocation. Step 2. Attack of the carbocation. And step 3. The formation of alcohol. The only way oxygen can have 3 bonds is by having a positive charge. The addition of unsymmetrical alkene is as follows. Take propene as an example. When propene is added to HOH or steam, you get propan-1-ol as a minor product and propan-2-ol as a major product. Addition of halogenation. Reagent is halogen in tetrachloromethane or aqueous. Condition: room temperature in dark. Product: halogenoalkanes, that is alkanes with halogens. When ethene is bubbled into bromine in CCl4 at room temperature in the dark, Br is added across the carbon-carbon double bond. The brown color of bromine is decolorized. 1,2-dibromoethane is produced. Ethene plus bromine. Bromine, which is brownish red in color, will go colorless when it becomes 1,2-dibromoethane. The mechanism of this reaction is as follows. There are 2 steps here. First step is trying to form carbocation. Second step, Br- attacks a carbocation to form dibromoethane. When ethene is bubbled into aqueous Br2 at room temperature in dark, 2 products are obtained. 1,2-dibromoethane and 2-bromoethanol. Test to differentiate alkanes and alkenes. Bromine water is used to test for the presence of the carbon-carbon double bond in compounds. The compound to be tested is shaken with bromine water. If it is unsaturated, the bromine water will be decolorized, as you can see here. The next reaction is oxidation by cold and dilute potassium manganate 7 solution KMnO4. Reagent is potassium manganate 7 solution. Condition: room temperature. Product: alcohols or diols. When ethene is reacted with cold dilute acidified KMnO4 solution, the purple color of KMnO4 is decolorized. Ethane 1,2-diol is produced. You can see the reaction over here. This is a redox reaction. The carbon species is oxidized while the oxidizing agent is reduced. This is another test used to differentiate alkanes and alkenes. Only alkene will decolorize the purple color of KMnO4, whereas alkane will not. And the next reaction is by hot and concentrated potassium manganate 7 solution. So the condition required is room temperature, and the product is going to be carbon dioxide, carboxylic acids or ketones. When an alkene is reacted with hot and concentrated acidified KMnO4 solution, the carbon double bond carbon in the alkene ruptures. The purple color of KMnO4 is also decolorized. The product formed will differ according to the position of the carbon-carbon double bond. If there are two alkyl groups at one end of the bond, that part of the molecule will give a ketone. For example, here the example is shown. You get two ketone molecules. If there is one alkyl group and one hydrogen at one end of the bond, that part of the molecule will give a carboxylic acid, which is shown here. First product formed is an aldehyde and a ketone. Aldehyde is further oxidized to ethanoic acid or a carboxylic acid. So the net effect is a carboxylic acid and a ketone. If there are two hydrogens at one end of the bond, that part of the molecule will give carbon dioxide and water. The example equation is shown over here. The last reaction of alkenes is addition polymerisation. A polymer is a long chain molecule made up of many repeating units. The small reactive molecules that react together to make the polymer are called monomers. Alkenes can open up its carbon-carbon double bond and join with each other in a long chain to form a polymer. As you can see here, addition polymerization of ethene. Ethene gives polyethylene. The displayed formula is also shown here. The section of the polymer shown in the brackets is the repeat unit of the polymer. The next example is addition polymerization of propene. NC3H6 gives a polymer polypropene. The displayed formula is also shown here. And the next example is addition polymerization of chloroethene. Chloroethene is otherwise called vinyl chloride. So the polymer which you obtain from here is called polyvinyl chloride or PVC. The displayed formula is shown over here. And that's all. Thank you so much for watching this video.